And I would like to request our sir to give flower and memento. And a humble request to all the students, please keep your mobile on silent mode. I express my gratitude to our esteemed Vice Chancellor, sir, for organizing this event. On the behalf of our JIS University, I, Devmitra Ghosh, extend a very sincere welcome to you all. I feel privileged to open this event. The university has a mission to be one of the top class university in India and a preferred destination for students, research scholars, and faculty members. Education in today's world has become industry need oriented, and it requires teaching methodologies to be fashioned in such a manner that suits this requirement. GIS University contributes to the growth of higher education, research, entrepreneurship, and skill development to blend traditional methods with modern technology enabled teaching and learning practices and modern technology enabled teaching in research and development. What you see today is the accumulation of massive continuous effort put in by the students and teachers. Our Honorable Vice Chancellor, Sir, Professor Indrajit Sengupta will address now. His speech will not only just be a collection of words, but a strong motivational speech to everyone. Thank you. Sir, please.
Thank you very much. Well, we are really privileged today to have Professor Rolf Dreschler among us today. So you already have seen his profile, many of you must be. So of course, we'll be having a formal introduction of Professor Dreschler very shortly. And you can see he will be talking on in the posters which are placed outside this building. He will be talking on some aspects of formal verification, polynomial formal verification. To set the platform in the proper sense, because many of you may not be familiar with this area, just imagine that we have an automobile manufacturing plant where cars are getting manufactured. So what happens during manufacturing? There is mechanical assembly, electrical assembly, so many other things goes into it. There are a lot of electronics also nowadays goes into it, IoTs. Now, after the manufacturing of a car is complete, someone has to thoroughly test it before it is sent out to the market for sale. We call it quality control. Now, in terms of circuit design, where he is an expert in, we call this process as testing. Every piece of hardware you manufacture, they must be tested before they can be sent to the market for actual use. Now imagine that the cars are getting manufactured, but in terms of the design, there are some defects. The braking system, the airbag system, the anti-locking system, the engine, there may be some design problem in any one of these. Now, what happens when there is a design problem? All the cars that are manufactured, they will be coming out, rolled out with those defects in them. They will all fail in some environment or the other. Similar things can happen in a circuit design. We are designing something, but assume that our design itself is defective. So whatever we fabricate, whatever we manufacture, each and every such unit will come defective. We need to protect against this. This is something which you call as verification. Now, verification normally we can do in multiple ways. We can do it through simulation. We can do it through something which we'll be talking about called formal verification. Mathematically, we can prove in some sense that a design is correct or not. So at least we need not have to worry about the correctness of the design. Okay. Now, the title of this talk says polynomial formal verification. Formal verification is a difficult problem. But the semiconductor industry, the VLSI industry recognizes that it is a very important component inherent in design and manufacture, so everyone has to go for it. There have been lot of efforts to speed up the process of verification. Normally, the complexity is exponential because the search space increases very rapidly. So what he will be talking about, certain kind of designs, if we want to verify, can we do it in polynomial time and also within limited resource constraints? So I hope I have put the context in a correct way. So we are all here not to listen from me, but to listen from Professor Dreschler. Let me tell you, he has been in India this time only for 5 days, and he has been kind enough to spend this one day with us today. So we should be extremely thankful to him. I would request Dr. Kamalika Datta, some of you may be knowing her. She was an associate professor in the Department of Computer Science and Engineering till a couple of years back. Now she is doing her postdoctoral research under Professor Dreschler. I'd request Dr. Datta to briefly introduce Professor Dreschler before he can start his lecture. Please.
Thank you, sir. A very good afternoon to all of you. So it's a great pleasure to welcome Rolf here in to JIS University. He was here for last couple of days, last 5 6 days, and this is his third talk. Okay, he already delivered two talks in IIST Shipur and at Kolkata University. So this is his third talk here, and many thanks for coming here to deliver this talk. So briefly talking about Rolf, Rolf Dreschler is a full professor and head of the group of computer architecture at Institute of Computer Science at the University of Bremen, Germany. In 2011, he additionally became the director of Cyber Physical System Group at German Research Center for Artificial Intelligence, which is called Deutsches Forschungszentrum für Künstliche Intelligenz in Bremen. His current research interests include the development and design of data structures and algorithms with a focus on circuit and system design. He is an ACM distinguished member and an IEEE fellow. He's also the co-founder of Graduate School of Embedded Systems, and he is the coordinator of the Graduate School System Design funded within the German Excellence Initiative. He is a co-founder and the spokesperson of the data center at University of Bremen. So I would say that if you have queries regarding circuit design or in a broad area of this topic, you can even directly write to him anytime and he will be glad to reply it back. Thank you. So all yours, Rolf.
So, microphone. It looks very nice, but I leave it off for the talk. Does this microphone work? No, not yet. It's switched on. Another one. Okay, this one. So, brief sound check. Can you hear me in the back? Yeah, that's okay. Perfect. So. Welcome, everybody. And yeah, thanks a lot for the very kind introduction and the perfect motivation. Yeah, because you were asking, hopefully this is right, is perfectly right. Yeah, it is exactly what we are doing. Yeah, so I'm very happy that I got invited. Thanks a lot, and I can talk to you today. So my name is Rolf Drexler. I'm from the university in Bremen in Germany. And this is not the first time I'm here in India. I've been in India quite a time before, so it's nice being back. When you see me here, that's a younger version of myself. Yeah. So I came here the first time in '94. Many of you were not born at that time. Yeah, so I visited there as a PhD student, a conference, VLSI design, that is very, very famous in our field. And then for me, this was a very exciting moment because it was my first trip outside Europe. Yes, that I came to India, traveled then through India for more than a month with a backpack. And of course, this was an interesting time for me, but why I'm telling this to you? Because at that time, of course, my family was interested to know how is he doing. Yeah, and during the whole time of this more than 1 month, I called 2 times home because it was difficult to get connection. Yeah, so these days I'm here with my mobile. Yeah, 5 minutes after I landed, I can text home. Yeah, so times really changed. Yeah, and that is what we always have to be aware of, how much we, with our technology today, change the world. I'll give you one example. This is the papal election. You might know that a pope normally gets only elected if the old pope dies. Yeah, and that was the case in 2005. And then what normally happens then is all the Christian, the Catholic people are waiting for the new pope to get announced. Yeah? And then thousands of people line up in Rome and wait. Yeah? And that was the picture of 2005. And you might see here, otherwise there's one person holding up a cell phone. At that time, we had these flip phones, yeah, so 2005. And very likely, this person was doing a picture. In 2013, the next pope got elected. This was less than 10 years later. The same situation looks like this. Yeah? So we should always be aware we are changing society. Yeah, with the technology, this normally from day to day changes. Yeah, so it's not so much that we are aware of this. Yeah, but when you look back, what was 10 years back? What was 20 years back? What was 30 years back? Yeah, if we look at, for example, at what are the big companies these days? It's Google, it's Facebook. Yes, how old are these companies? Because you would be surprised. Yeah, I'm older than these companies. Yeah, and I'm not that old. Yeah, so believe me. Yeah, so. And that is with this technology. Yeah, so we have technology everywhere these days. Yeah, so we have technology with the smartphones, with the computers, and this is really what are also the most challenging professions of the future. Yeah, so computers are all around us, but when we really nail it down and see what is the core component, these are computer chips. Yeah, this is where we find them in this kind of electronic device. We often, in the Professor Indranil Gupta gave a perfect example with autonomous driving. And so when we look at modern cars these days, and of course I'm from Germany, in Germany, like Mercedes, BMW, Volkswagen, Porsche, there are many, many car manufacturers. Yeah, these are high-speed computers these days. How many processors do they have on board? 5, 6, 7? No, 250, 300 processors in one car. Yeah, so the computational power you have in one car these days is amazing. Yeah, you have sensors all around. Yeah, so if, of course, connectivity. Yeah, so when you look at the high-end cars, also like in planes, of course, and also when you look at future technologies, yes, we can expect that this will even improve. And what was also very nicely given as an example before is that when you think in terms of self-driving cars, also the components we use today, like airbags, braking systems, and so on, of course, we trust that these components work. And we also hope that our cell phone works. Yeah, so if we cannot text something, we are a bit angry, upset, or whatever. Yeah, so but normally it does not change our life. Yeah, but if the car's components are not working, that's a real issue. So this is a slide that you have seen in one or other way before. Yes, that is Moore's law, and that is something that is driving this industry for many, many years. So when we look at the early 70s, there were, can hardly see, so please hear what I'm saying. So it's like in the early 70s, We had the first microprocessor produced by Intel. They consist of a few thousand components. In the meantime, the circuits that we built, yes, so there's a logarithmic scale, so this means exponential growth for many, many years. These devices nowadays have up to 50, 100 billion components. So it's the most complex systems that humans are developing. Yeah? And now the challenge is, how make we sure that this is done correctly? Yeah? So how can we verify that the system is running properly? And so this kind of curve is flattening a bit. Yeah? So in the high times of technology development, we had this kind of improvement regarding the complexity each 18 months, doubling the complexity. Well, nowadays this flattened a bit. So in the sense that now we have 3 to 5%, yes, but still these are very, very complex systems. So when we keep in mind, what is the challenge? The challenge is, like, we had these early processors with a few thousand components, run at very low frequency. Now we have 10 billions more components at high clock frequency with gigahertz of clock speed. How can we make sure that these systems are running correctly? You could simply say, okay, let's try it out. Yes, whenever we have a simple system, we try out all the possible combinations. Yeah? But these systems are so huge, you have no chance of ever trying out all the possible things. Yeah? If you would try to find out all the possible combinations what your cell phone can do, you would have to download all the possible apps in the world. Yeah? So this is not doable for you. Yeah? So we want to ensure correctness. And the simple thing, and that's what probably many of you also when you are in a lab or so run first, is simulation. Yeah, for example, you build a circuit that should do, like a calculator, the addition. Yeah, and then you say, okay, let's try out 2 plus 3 should be 5. Yeah, then you apply 2 at the input, you apply 3 at the input, you see 5. Now you know that it works for 2 plus 3. But does it also work correctly for 4 plus 4? You don't know. Yeah? And that is something, maybe I can, a door we can close? No, we cannot. So there's the option of having this kind of test vector that you apply. But the difficulty is, even if you apply 1,000 test vectors or 100,000, this is nothing compared to the complexity of the system. Yeah, so the coverage you get is very low. That's one of the difficulties you have. Yeah, so, but nevertheless, as has already been said earlier, you have to do verification. Yeah, the alternative would be, so say, we don't build circuits anymore. Yeah, but of course you want to build them, and you want to build them as good as possible. So you can buy so-called hardware emulators. You can buy computers that are highly optimized for doing simulation. Yeah, they give you a speed up of 100x, 1,000x, but still the coverage is very low. And here, when we talk about functional coverage and correctness, we really want to make sure 100% correctness. Not 80%, not 90, not 99.9, really 100%. And the only ways how to do this these days is so-called formal verification, that you prove in a mathematical sense that a system is running correctly. And that's exactly, I assume not all of you or hardly any will be experts in formal verification here. Yeah. So, but I show you how these systems work, give you some examples for this, that you get an understanding. Yeah, and then finally, I'll also show you what is the latest development in this field, yeah, so that you see what current research is doing there. So the major motivation is that we want to really ensure 100% correctness. Yeah, so everything that is below 100 is not satisfying, it's not okay. And that is exactly what companies like Intel, AMD, and in Germany also Bosch, Siemens, with whom we are collaborating, yes, is exactly applying. And so there are two main tasks. One is equivalence checking, and one is so-called symbolic reachability analysis. Equivalence checking means that you have a specification given and an implementation, and you want to know whether this matches. Yeah, someone says, like, build an adder circuit, and you do a design, and now you check, is this an adder, yes or no? This is the equivalence checking problem. The other one is symbolic reachability analysis when we deal with sequential problems, yes, that have some kind of timing behavior. Then the problem, in some sense, even becomes harder. You model this as so-called finite state machines, what you might know from the theoretical world, yes, and this is the core of the tools like model checking or property checking. First of all, the bad news. The bad news is, in some sense, that we can prove that these are hard problems. Yeah, so it can be formally proven that there will not be, unless this P is equal NP, what is pretty unlikely, that there will be not a single algorithm that can do a polynomial solving of all these instances. But my talk is entitled Polynomial Formal Verification. So this might sound as a contradiction. Yeah, so because what can you do? Because you can prove that you cannot do it polynomially for all the instances. But my question is now, maybe you can solve relevant subclasses efficiently. We are not proving P equal NP or so. Yeah? So it's not like we are addressing the overall problem, but very relevant subproblems. And that is here. So in the following, I'll address this combinational equivalence checking. That means that you have two instances given, and you want to know whether they match. And now, these problems can be solved, yes, if you have exponential time and space. If you have arbitrary resources, then you can solve them. Yes, it's not that it's impossible to find a model for this, but the problem is that the runtimes, you want to bring your product as early to the market as possible, so you cannot simulate your design for 100 years or so. Yes, you want to have this done until hopefully next week or so. Yeah. And that is that you have short runtimes. And now the question is, can we get this completeness, but under resource constraints? And the resource constraints are what we in the following address as this kind of polynomial upper bound for the computation. So what is the overall goal of our research work? So far, verification is often done as some kind of post-processing. So classically, the verification comes after the design phase. Yeah, it means that someone does a design, also in companies. Yes, you have the group that does the design. They hand it over to the verification group and say, please check whether I've done a good job or not. Yeah, so it's some kind of post-processing. And typically the designers by this do not focus on the verifiability themselves. Yeah, they are design focused. And the drawback here is for sure that by this, there's no guarantee that you finally can do the verification at all. And it really happens that someone does a design, then it is shown that it cannot be verified, and then you need a redesign. And this is, of course, very costly. Yeah, and this means that also the tools that you can buy today, they are unpredictable in the performance. Sometimes they give very quick results, you start them, but sometimes it takes more or less forever. And of course, that here the required resources are typically unknown. And that is exactly what we address with this field of the polynomial formal verification. So that you have some kind of space and time complexities, but they are polynomially bounded, that you have some kind of upper bounds for this process. And the far-reaching goal will be that at some point that we can have the verification also as some kind of key component during the design. And that would mean that we replace this pure design-centered by verification-centered approach. And by this polynomial verification would be an additional design parameter. Of course, you still want to have fast chips and small chips and chips that do not consume too much power. Yeah, so normally chip design is some kind of multi-dimensional optimization. Also, these resources can be predicted and, of course, then have shorter time to market, and finally also would have some kind of better results. So in the following, I'll only look at this combinational equivalence checking, what I said. So there's also a sequential variant of that, but we are keeping it here simple. This is a mixture, of course, of theory, yes, where we have this kind of polynomial upper bound. We prove something in a mathematical sense. We develop the algorithms, but it's not only theoretical, but we also implement it finally, so that we have really tools that we can start and that do the process automatically. Because, as I showed before, we want to verify circuits with 1 billion components. You cannot do this by hand. Yeah, you will not prove something by hand with 1 billion components. This can only be done by computers these days. And the goal here, of course, is that we want to have some kind of optimized time and space bounds with the smallest possible polynomial orders. This means, like, whenever we talk about polynomial, yeah, we mean something like n to 2 or n to 3. If you have something like n to 100, this is also a polynomial, yes, but it would require long runtimes. Yeah? So we want small polynomials. And of course, whenever you do this kind of complexity theory, this is this O calculus, where you have this kind of constants that got ignored here. This is very relevant. And what is especially important, we want this not only for the final representation, but for the complete intermediate construction. Okay, so this was more like the motivation part. I hope you're all motivated. Yeah, so you want to now know how it works. Yeah, how does verification work these days? Yeah, and that is, first of all, I can say this is not something that is totally new, because formal verification, this idea was born in the late 80s, early 90s. Yeah, so it's not like formal verification is something that is just there for 5-6 years or so, but it was always known to be very runtime consuming. But on the other hand, it's the only technique that allows this 100% correctness. Yeah, so this was always the trade-off. Yeah, so already in very early years, people observed that this kind of peak reduction, yeah, so the memory peak that you need during the construction, that this is somehow the bottleneck of these approaches. And that's a picture that I took from a paper from 96, yeah, so quite some years back. Yeah, so already there, people saw that sometimes representing a function, yeah, in terms of memory, here for a specific data structure called BDDs, at the output it's small, but in between it is large. And now in the following, and that's very typical for these techniques, that you sometimes need a lot of memory consumptions, and then at the end, it becomes smaller again. And now so that's what we studied in my team for the last 20, 30 years. And in the meantime, we had a very good understanding where this comes from. And that's exactly what I wanted to show you with some examples. Yeah, and that you understand what is verification in general and how do these techniques work these days. The first time polynomial formal verification was really applied is, in the meantime, 20 years back, but that was only theoretically. So no implementation, no automatic tools. Yeah, but this was something where this has been studied for the first time. Before I come to my example, one very, let's say, famous circuit design, yeah, so that you can see how you can do verification or testing in general. I don't know, who knows this circuit? Intranet should raise his hand, he knows for sure. Yeah, so okay, very few. Yeah, so that is called a mitre circuit. Yeah, whenever you have two circuits, yeah, and you want to make sure, are they computational the same or not, you can connect them in such a way. Yeah, and this means not only the students should switch off their phone, yeah, so also the professors. So we have two circuits, they are connected here, and this means that we apply the same inputs to both of them. Then we connect the outputs with XOR gates. And an XOR gate has the property that if the two inputs are equivalent, it says 0. If the two outputs are different, it gives 1. And there is an OR gate at the output. So now, if circuit 1 and circuit 2, for any input combination, show a different behavior, this output will become 1. Because let's assume that I have assigned input so that the first output is different. Then I have a 0 maybe here and a 1 here. This means that there's an output 1 here and an output, if any of the inputs of the OR gate is 1, then the output is 1. And so this is a reformulation of the problem that we say, like, for this kind of circuit, If the output here is constant 0, then these two circuits are equivalent. Yeah? And so I can reformulate a circuit problem to a set problem, so a satisfiability problem. Yeah? And representing a constant 0 at the output is easy, but checking whether the two are really different, yeah, that is difficult. Okay, now I look into, let's say, a non-trivial example. Yeah, so how is verification done with automatic tools these days? And for my example, I took multiplication. Multiplication is something that you find in each calculator, yes, in each processor, everywhere you have multiplication. Yeah, of course, more recently also in signal processing. If you look in cryptography, more recently we find many of these AI chips. Yeah, so you can have some kind of accelerator boards that are fine-tuned for multiplication for running your neural networks applications. Or if you're interested in data science application, that's the core algorithms you need. All the techniques that we know for these bit-level approaches, binary decision diagrams, term rewriting, submodular theory, whenever you start these tools today, they all fail. And how can we do formal verification for multiplication? And that is a technique that is called symbolic computer algebra. And now I'll show you how it works. And this one is scalable for what I called here clean multipliers. Yeah, so it depends on, for some multiplication implementation, this works well. For others, it does not. And I'll give you examples for which this works. Yeah, because in the meantime, we have a pretty good understanding how these techniques really work in practice. Yeah, so I'll give you this SCA, this symbolic computer algebra in a nutshell. Yeah, so that you, after 4 or 5 slides, you will understand how this technique works. Yeah? Here's a netlist on the right-hand side. And now I'm claiming this is a 2-bit multiplier. You can believe it or not. Maybe it's an example where I show that it's not the case. Maybe it is. Yeah. So what can you do? Yeah, because it has only 4 inputs. It's a small circuit. You could just simply do simulation. You could simulate all the possible values. Yes, 0, 0, 0, 0, 0, 0, 0, 1, and so on until 1, 1, 1, 1. You simulate all the 2 to 4, all the 16 possible combinations, and then you would know whether it works or not. But of course, this technique would not be scalable. Yes, if I then would give you a 64-bit multiplier, then you could not do it. Yeah, so that's why I now show what is the approach, and this, let's say, the core of the lecture here. Yes, of the presentation. Yeah, so here that's where you should now get an idea of how the techniques internally work. So in general, we are claiming this is multiplication. So this means that this set is A times B. Yeah, so this is our specification. That we know that we have set is A times B. And if we substitute that or subtract, then set would be the same as A times B. And this is equal to 0. To show this here for the operands, yeah, so A and B are the 2 operands, A and B, and Z is the output. And now, since this is some kind of binary encoding, yeah, we would have like, this is set 0, this is 2 times set 1, 4 times set 2, and 8 times set 3. Yeah, so that's the output vector in a binary encoding. And for the inputs, we also have these values of B0, 2 times B1, A0, 2 times A1. Now, it's the question whether this is the specification. It is a multiplication, and this is a netlist. And now that's what we call the specification polynomial. That's the polynomial that describes the multiplication. And now the specification and the netlist, they are equivalent exactly if the remainder becomes 0 when dividing this by the gate polynomials. This sounds a bit weird, a bit complicated. Yeah, so I'll show you in an example what this means. Yeah. For each of the gates, we have to define what the kind of polynomial description is. Let's start with the, let's say, simplest gate you can think of. That's an inverter. someone that inverts a function. And that means that if, and this can be described by the following formula, f is 1 minus a. If a is 0, the output is 1. If a is 1, the output is 0. Yeah, that's just the complement of a function. Now we have a times b. Namely, that's the AND gate. F is a times b. Yeah, because only if both inputs are 1, the output is 1. For the XOR gate is a plus b minus 2ab. And here it's important that this is not a Boolean formula, but it's really a polynomial description. Yeah? So if you enter here for a and b is 0, it is 0 plus 0 minus 2 times 0 is 0. So that's exactly the value of f. And if one of them is 1, it's 1 plus 0 minus 0, it's 1. And so you can directly see that this is the correct functional behavior. And the same for the OR gate. So this means we have these kind of polynomials that represent each of the internal gates. And now what this kind of formal verification does is, for here our integer multiplier, this we go from the outputs to the inputs and substitute each of the values. And this now means that we start from the outputs, we go in reverse topological order. And here what we have is exactly the polynomial that I showed before, the specification polynomial. Yeah, that's 8 times Z3 plus 4 times Z2 plus 2 times Z1 minus the a times b. And now we start here at the output with Z3. And we substitute this Z3 here by G1. So G1 is an AND gate. So we know that this is just a times b. And this means that he substituted here with W1 and W4. Yes, and this means that we here substitute now the Z3 variable by this value. Now we go step by step from the outputs to the inputs and substitute each of the values. In the next step, we would substitute this G2. And if we do so, what we see, this is the most relevant observation. Yes, for a small example, here we have 8 times W1, W4 in positive form, and here we have it in negative form. And this means like we generate something and that gets canceled out. That's important, yeah, because that is exactly what formal verification does. It generates these terms, and now they reduce, and if it's a correct circuit, it will reduce to 0 at the end. Yeah? And that is exactly what, when we continue this process, now we go all the steps up, then we'll see that this is really 0, and this means this is really a multiplier. It's bug-free. And then we are happy. Yeah? So that's the great time of the day of the verification engineer. Yeah? And then you feel excited, yeah? Because you have done the verification job. And now this is like what we have briefly seen here, yeah? Because what this means, think in terms, I am a computer, I am an algorithm, yeah? So I generate something that gets canceled out. That means that I had to allocate some memory and then I can free it again, yeah? So, but at the end, it will become 0. Okay, now we keep this in mind and we look at multipliers. Yeah? So whenever you have a lecture on multipliers, yeah, so how to design multipliers, typically multipliers have some kind of 3-stage structure. You first generate partial products, you add up the partial products, and you have a final stage adder. Yeah, that's the typical way you add this. Yeah? Some of you might know these architectures. As for the others, just believe me. Yeah? So I know what I'm doing. Yeah? So, and how the different multiplier architectures differ is essential how you build these 3 stages. And now, for example, here in the first stage, you can do this by a simple partial product generator, what is essentially an AND gate. Or you can do some kind of boost encoding. For the partial product, you can have array-wise addition. You can also have some kind of tree-like addition, like Wallace tree, Dada tree, compressor tree, many, many variants. And Finally, you add up with an adder. This can also be the ripple carry adder, carry look ahead, Brett Kung, many different things that have been introduced over the last, I don't know, 50, 60 years. Yes, addition is one of the most elementary operation. Yeah, so this has been done for a long time. Okay, so what is the most trivial or simplest multiplier you can think of in the way that you take always the first out of each of the blocks? Yeah, you take these AND gates, you do an array addition, and you do a ripple carry adder. Yeah, but this is very slow. Yeah, because it is a linear array and a linear adder. Yeah, so but this is I'll call this in the following the trivial multiplier. Yes, that's the easiest one you can think of. Yeah, but it has so it's this kind of partial product generation, array, and ripple carry. But it has an interesting property, namely that all the elements in the second and third stage, they consist only of half adder and full adders. So this design is very regular, very easy. Now I call this a non-trivial one, a little bit more complicated one. I do the same in the first stage, this partial product generation, but then I use a Wallace tree and a carry look ahead. So those of you who don't know these architectures, there's just more complicated ones, and they have the property that they do not consist of half adders and full adders. Yeah, they have some kind of other structures, more irregular structures in between. Now let's look at this only algorithm from an experimental point of view. Before we had a 2-bit adder, 2-bit multiplier. Now we look at a 4-bit multiplier, and now we exactly do this kind of substitution, this backward process, and look at what happens experimentally. Then we see that this kind of simple, this trivial multiplier needs almost no memory in between, and finally goes to 0. In the correct case, it's 0 means this is the correct multiplier. And this means in number of monomials, it needs around 30 terms. And the number of terms somehow corresponds to the memory requirement in between. The other one needs here almost twice as much, yeah, so that you have something like 60 terms. But 4-bit multipliers are boring. These days we build 64-bit. Yeah, so now let's not look at 4-bit. Now let's look at 8-bit. What happens then? And then you see what exponential blow-up means. The blue line, again, 8-bit, pretty trivial, while the other already here needs 100 terms. This already means here 1 million. Yeah, really significant amount of memory. I mean, we are computing this with machines with 256 gigabyte or larger. Yeah, so I mean, this more, but whenever you have exponential growth, this will reach some limit. And of course, if we go like for the next level for 16-bit, the blue one can still do it, while the other one here explodes. Yeah, so you cannot verify this more difficult multiplier. And this means like it's not a question in general, can we verify multipliers or not? It's about what kind of architecture do they have. If we have a smart, a good, a clean architecture, you can do the polynomial, the verification. Otherwise, you can't. And the reason here, this was purely experimental, is the explosion in the number of monomials, even for small and non-trivial multipliers. And the reason for this is what we call in our community so-called vanishing monomials. These are the ones that you have to generate, but they cancel out, or they disappear after a while. And that's exactly the difficulty that you have to face, that in between, memory is consumed that is not used at the end. So this is purely experimental. So with some kind of fine-tuning, in the meantime, using these techniques, we can also verify techniques, verify multipliers with a few 100 bits, where when you compare this in commercial tools, they all fail. Yeah, so this is something that we can do efficiently these days. And when you look at this kind of vanishing monomials, yes, for some architectures, it's almost 0. Well, for others, it grows, yes, but you can still control it. But this was only experimentally, so we had no polynomial upper bounds. We have never shown that the resources we need are limited. And this is exactly what the goal of our current research is. Since you're not expert in these formal backgrounds, I'll walk you through this a little bit quicker, yes, but I give quite a number of references. Yes, so if you're interested in that, then you can get some kind of further information in that. So in this sense, this is the trust me part. Yes, where you have just to trust me that this is correct, and this is not meant to be fully understood. Yes, but that you get the core idea. How can this be done? Yeah. And here, a very popular data structure in this context are so-called BDDs, binary decision diagrams, introduced by Brian in the mid-80s. And what you do there is that you generate BDDs for the inputs. And what now the difference to the simulation that you are using is that here you are not applying zeros and ones, discrete values, but symbolic values. You're calculating with the symbolic values. You propagate these BDDs, these symbolic values for the circuit, and then you evaluate it towards the outputs. And you do this kind of internal operation for these blocks. For BDDs who want to experiment with this, you can download many free BDD packages in the internet. Yes, so this is freely available. And then they are based on a so-called if-then-else operator. And based on that, you can formulate each of these internal gate operations then in terms of this if then else, and this one also has a polynomial upper bound. And now what we have done, and this started around 3 years back, that we started with a circuit structure that is very well understood, namely adders. Yeah, adders are in some sense non-trivial, but the most simple one you can think of. And it was known for BDDs that they have a linear size for the adder function. That was known before. But for the final representation, now we look in the verification process that also the memory peaks never become larger during the construction. That is the important part, yes, that we really want to see the verification always has an upper bound regarding runtime and memory requirement. So we considered here some kind of different adder construction like ripple carry, conditional sum, carry look ahead. First, only giving some kind of polynomial upper bound, but not calculating the exact complexities. And that was done in some kind of follow-up work that we considered this, gave the exact bounds, then this kind of polynomial formal verification can be applied. And now experimental results show that you remember we had this for multipliers, we had 4-bit, 8-bit, 16 bits, and then it explodes. Here now we can do 1,000 bits in no time. We can calculate 10,000 bits in 200-300 seconds. Yeah, so these are really scalable approaches, because nowadays it is still that often the design people are ahead of the verification people. Yes, that you have difficulties in verifying 64-bit designs, but so far not many people are building 10,000-bit designs. Yeah, so that is more the next generation. In cryptography, we sometimes have 1,000 bits or so, but this is really rarely. So this also confirms the theoretical calculations. And now we apply this to a whole set of different adder architectures, like this prefix operation. That is, you can add this up serial or in Lardner-Fisher principle or Cogger-Stone. And this is all here more or less the same, that you can, with different polynomials, but you can prove also polynomial upper bounds in these cases. And when you do the experimental setup here, then the verification runtimes are again that you can scale this up to 10,000 bits. And the runtimes vary slightly for the different architectures, but in principle, that is all then working properly. Of course, the whole world does not consist of adders only. Yeah? So what is nice, it's a first step, and it shows that even though you're dealing with an NP-complete problem, yeah, it is proven to be a difficult problem, but for the subproblem of adders, you can do this efficiently. Now the question is, can we expand that? Can we go beyond this? Yeah? And that is now, of course, the first thing you can do is an ALU. So also for a simple one, here this kind of, if you would apply these BDDs that I just shown straightforward, that would fail. But you can do what we call partial simulation. That means that you do not simulate everything symbolically in one step, but one after the other. And then, but in a finite number of steps. And this then also shows that this is doable. An architecture that is very popular these days is the RISC-V. Maybe some of you have heard of that. So it's a free and open instruction set architecture that comes with different bit widths of 32, 64, 128. And what makes it very interesting is this kind of modularity and extensibility. So you can generate this core in different sizes. So what means that you can have a very simple integer instruction-based architecture. You can also add some kind of arithmetic like multipliers. You can have floating point and so on. And now we come here to, let's say, also also a little bit of a view to the future, because the papers on this, they are going to be published. So this is very recent research here, that we at this time we do this kind of verification of the RISC processor, and this is also doable with partial simulation, with simulation, and also with a polynomial time complexity. This is not, let's say, a full-fledged RISC architecture in the sense that it can handle all the configuration, but the very simple one. Of course, now we are looking also at things like this floating point. That floating point, the number representation, of course, is then highly relevant in the sense that you always, for a very specific design, for a very specific architecture, then this can be considered. Again, here, also theoretical studies shows that in general, this will become exponentially large. So, and it will not work for all the possible implementations, but what you can show is that if you do a clever case splitting, then for a given architecture, you can also show a polynomial upper bound, what will be shown at date this year. So this is now the, let's say, the edge of research. Here's what we are currently doing, and what we will also then consider in the future. Also some more ideas when you implement polynomials, yes, like here x and y are some kind of larger scale polynomials. It's also that this kind of BDD techniques, these bit level techniques will fail, but there are some kind of word level operation. Yes, we can also include word level proof techniques in these engines. They can handle these and can work with this efficiently. Here it is also that, for example, they can prove that they have quadratic time, but you have to be careful in the sense that when you apply this, for example, to a polynomial x to 3, this would then have a space complexity of n to 3, but a runtime of n to 6. And n to 6 is still polynomial, but it is pretty large. So if you now insert that with a million gates, a million to 6, yes, is larger than you can handle. And there's something you have always to be careful. That polynomial on the one hand side is nice, but also that you deal with the right polynomials. This is why we also have this kind of experimental evaluation and validation, where you can then see also this kind of runtime and memory requirement. Okay, and this means, like, for the general problem, it will be not solvable. That's clear. So because it's an NP-complete problem, that's not the point. So you need some kind of additional information. And this can either be some kind of structural information. For example, you know that the circuit has a tree-like structure, or it has some symmetry properties. And finally, I'll give you an idea what we are currently working on. So also what we're somehow looking towards the future. So what is we want to know, and that is especially to use some kind of hierarchy information. Because if you have a design, then it's typically described in some hardware description language like Verilog, VHDL or so. And this means that here you have also then this kind of replacement of subcomponents that you can do, because you know what are the corresponding blocks that can be used also for the verification process. And here we use then these kind of hybrid proof engines. It will not be the case that we have one proof engine for all of them, but that is some kind of hybrid proving. So how this can be done, also coming back to this multiplier example. So a complex design in Verilog VHDL consists of many, many subcomponents. Then it will most probably not be the case that you have one monolithic proof for the entire design, but you split it up in various proof parts. Yes, and this means that you have a hybrid proof engine. That means like you have some parts that work very good for the bit level and some very good for the word level. Yeah, and then you configure the proof process accordingly. For example, if we have this ALU that I showed you before, it's almost the same one as before, but I exchanged here one operation so that there's also multiplication included. This means that this earlier BDD-based approach would fail, but we know that multiplication can be done efficiently with the symbolic computer algebra that I showed you before efficiently. And this means like we can use the BDD part for some of this and the SCA part for the rest. Yeah, so it means like you switch them dependent on the respective operation. And so like this can be also done for multipliers. Now when we have the design requirements and we are capable for these clean multipliers. That's something we know from the earlier observation. Yeah? Now let's assume someone says, yeah, your multiplier is nice, you can verify it, but it's not fast enough. So we need a quicker one. Yeah, so it means like we can also have these kind of verification steps that we split up. Let's assume we have this kind of multiplier that I showed before, partial product generation, addition, this accumulation, and the final stage adder. And now we know that this final stage adder, this is the difficult part. Yes, it's fast, but we cannot verify the entire design. What we now can do is that we cut off this part, we move this aside, we substitute this by a simpler one, maybe a ripple carry. Now we can do this proof, but now one might argue, okay, but you're not verifying the right design, yes, because you exchange something. Yeah. Now you on the one hand side you verify this anti, and then you verify that these two adders are the same, and then you have done the complete proof. And that's exactly what you can do. That you say, okay, the goal is we can verify this simpler multiplier with some upper bounds. We can also do this kind of final stage adder. This has also to be done, and then we have the entire verification process terminated. So this shows that then we can apply alternative proof engines that are used. Okay, so this is ongoing work. Yeah, it's not that this is something that is finished. Yeah, so verification in some sense always ongoing. We can argue as, but here it is especially that we want to get a very fine-grained understanding of what are the tractable classes of combinational circuits in the context of combinational equivalence checking. And for this, we have quite a whole bunch of decision procedures. Here I showed you now these BDDs and symbolic computer algebra, but there are many other SAT solvers, SMT solvers, and so on. And once we have a better understanding of this, we also want to feed this back in the classical design flow, so that we can say to designers, if you use this architecture, we can finally do the verification. If you use this one, we run into trouble. Yeah. So, and of course, as a result, we are now looking at more complex case studies, as I just said. For a very simple RISC-V architecture, this is doable. But if you now include pipelining and also floating point multiplication, we know how to do. But there's, for example, there's also division. We don't know how to division yet. Yeah? And so there are quite a number of open problems. So this brings me to the summary of my talk. As I said, we started around 2020. Yeah? So this is ongoing work and will continue for some more years. There are first promising results, yes, that we show that the concept in principle works. Yes, but of course, we learn from more complex case studies and then have to also apply the best fitting solve engine, where in some sense the goal of all this is to have a correctness by construction. Yeah? So we already have the also established term in technology of design for testability. It would be nice to have something like a design for verifiability approach. Yeah, and there's a very high demand from industry on this. Yeah, so when you also look at job offers, either of the EDA companies or also of the companies like Intel or so, they are looking very intensively for verification engineers all the time. And so that's a very active research field. So finally, I want to thank the members of my group and especially the students working in this project because they significantly contributed to the results here. And this brings me to the end of my presentation. I'd like to thank you for your attention, and I would, of course, be open to questions. Thank you. Will someone moderate, or should I just ask for? Are there any questions?
Students are advised to ask questions if you have any. Or faculty members are also there. If you have any queries, you are free to ask.
I have a clarification, not really a question.
Yeah.
This kind of symbolic verification methodology, can we apply this for processor verification? Means, for example, the micro operations, micro instructions.
Yep.
So can we apply this technique to that kind of a?
Yeah, of course. You can do it either really on the net list or also on the symbolic level of the instructions. Yeah. So this is on all the levels, and finally that's also needed that for each of the, let's say, transformations you carry out, you finally want to validate whether you use a compiler or some kind of synthesis tool, whether this is running properly.
So as an extension, we can also verify certain algorithms.
This is correct. Like there's often the question when you do hardware verification, like I do, how about software verification? Yeah, this is in some sense much more harder. Yeah, because then you run into a lot of so also from a theoretical point of these undecidability problems. Yeah, whenever we have something like a for loop, we can unroll the for loop. Yeah, we know that this is a for loop of only some kind of 10 steps or so. Yeah. In software verification, you have a lot of undecidability problems, whether you can exit a while loop or so, and this makes it much harder. Yeah, so that's why, of course, these days we also apply many of the formal techniques. Let's combine them also in a hybrid fashion with some kind of software structures. For example, you use mutation-based testing, concolic testing, and also fuzzing. Yeah, so the techniques that people more from the software world use. And by this, for example, we were able also for RISC-V architectures to identify bugs in operating systems. Yes, where we combine this kind of symbolic techniques with partial symbolic simulation with the testing techniques. But then still you cannot get 100%. Yeah, but it's a very relevant problem, and that's why we are also working in this direction here. And of course, also was Kamalika Datta said at the beginning, if you have any questions or if you're interested in this topic, also on our webpage, you can find many articles or feel free to contact me anytime. So that's a very vital research area with a lot of application. And so if this finds your interest, please let me know. Of course. Okay. Okay. The question is the question is we do this for, let's say, classical CMOS. Yeah. So classical circuit design. Now, when we look at emerging technology, the question is how's about quantum circuits? Yeah. So also people look into quantum computing, and there it's also more about the modeling because you have not this kind of discrete states anymore. Yeah. You have not zeros and ones. Yeah. As long as you only look into discrete states, these techniques can easily be extended. Yeah, and there are also, like we have these BDDs here for decision diagrams for binary. There are also some kind of quantum decision diagrams, yeah, that can be extended in this direction. But this is also a focus of current work, how this kind of formal proof techniques can be applied there. These formal techniques like BDDs, what I showed, can also be applied in many of the design process, in optimization in general. Yeah, but also for quantum, that's also still something that is currently investigated. I'm not aware of any, let's say, polynomial formal verification of quantum. Yeah, so but formal verification of quantum in general, there are some groups working on this. Yeah.
Any more questions? If there is no questions, I'll request Professor Dhadube sir to please say vote of thanks.
Good afternoon, all of you. And just this is a wonderful session. Though I'm not from this area, sorry, but I would I would have really asked a few questions. But thanks a lot, sir, that you came here today. This is our real honor and pride for us, for this campus. The students are really, I think, enlightened by your great, delivery. And thanks to Dr. Kamalika, Professor Kamalika Datta. She has become a medium for our JIS University to bring Sir here for this wonderful delivery. And of course, I can't stop myself by not thanking our very Reverend Vice Chancellor, Sir. Under his leadership, really, I have seen this university grow like anything. And for this very great occasion today, and I thank you, sir, very much. I thank all my professors, my team, my students, and all people who are just behind this show, the backup people, everyone. Thank you very much. Thanks a lot. And also, there is one.
Yeah, I'll ask VC sir to kindly.
Yes, sir. Please. Thank you.
Just one last thing. Professor Dreschler is having his flight back today in the evening. So let us thank him once more for sparing his extremely valuable time and spending his time among us and enlightening us with his very nice lecture. And the thing is that he was given some flowers, but he cannot carry the flowers back home, unfortunately. So, on behalf of the university, there is a small token of appreciation which you can indeed carry back.
Okay.
This consists of a traditional Indian dress, which I'll not ask you to wear now, but please go back, wear it, and send us back a photo.
Thank you. So next time I can dress up appropriately. So thanks a lot. So, thanks a lot.
We'll have a photo session, sir.
Okay. So put this aside.
Controller, sir, please. Computer science faculty members.
Can you stand out there so that I can take a picture of your students? Okay, so now you have to smile. Yes, more important than this.
Kamalika ma'am.